The Skippy project aims to design, build and demonstrate a highly athletic monopedal robot called Skippy. This robot will be able to hop high, travel in any direction, somersault, balance on a single point, make accurate targeted hops, and if it makes a mistake and crash lands, then it can get up again unaided and undamaged. And it will do all this in 3D with no harness, no umbilical, no safety net, and no remote brain. The scientific objectives of the Skippy project is to test what we call the Skippy hypothesis, which is that it is easier to increase the complexity of a high-performance robot than to increase the performance of a highly complex robot. If this hypothesis is correct, then it implies that the right way forward is to achieve physical performance first and increase the complexity only after the desired performance has been reached. Here is a diagram illustrating the idea. Our ultimate objective is a robot that can replicate both the complexity of motion and the high physical performance of a human being, so that it can perform a wide variety of economically and socially useful tasks. Most humanoid designers have approached this goal by choosing to replicate complexity first. But Skippy takes a different approach. We seek to achieve the highest possible physical performance in a robot that is deliberately designed to be as simple as possible. Another special feature of the Skippy project is that Skippy is a technology-inspired robot rather than bio-inspired. In other words, we are not trying to copy the performance of a human or animal, but instead to reach the kind of physical performance that should be possible with today's robotic technology. In other words, the technology performance envelope. This is why some of Skippy's performance objectives are beyond what a similar-sized animal could do. Here is a conceptual diagram of Skippy. It is not to scale and the parts are not shown in their true shapes. As you can see, the whole mechanism is planar except for the crossbar, which rotates about the axis shown. Overall, the mechanism has 3 degrees of freedom: revolute joints at the crossbar and ankle, and a 4-bar linkage at the hip, which allows the leg to rotate relative to the torso. This linkage also provides a factor of 2 amplification of the motion, so that the lever needs to rotate by only 90 degrees in order for the leg to rotate by 180 degrees, which is its full range of motion. The crossbar and hip joints are actuated, but the ankle is spring-loaded, so Skippy has only 2 actuators, which is 1 actuator less than Raybert's pioneering 3D hopper. The main motor is responsible for making the robot hop and for balancing in the sagittal plane. The crossbar motor is responsible for keeping the sagittal plane vertical and for steering the robot in 3D. So Skippy's strategy for balancing in 3D is to balance in its sagittal plane and to keep that plane vertical. We call this bend swivel balance control, and it looks like this. In this animation, a Skippy-like robot performs a sequence of commanded movements while maintaining its balance using bend swivel control. The animation has been slowed down a little so you can see what the robot is doing. Only the 2 upper joints are actuated. Observe that the robot can turn to face any direction. This is how Skippy will steer in 3D. Back to Skippy. The main motor operates the hip joint via the ring screw and the main spring. The ring screw is a newly invented mechanical component that performs the same function as a ball screw, but can operate at much higher speeds. Skippy needs the extra speed in order to extract the maximum power from the motor. In fact, it was the need for extra speed that prompted us to invent the ring screw in the first place. Here is a picture of one of our ring screw prototypes. As you can see, the screw rod passes through a nut containing 3 bearings, each carrying a specially shaped inner ring which makes a pure rolling contact with the rod. We have tested a ring screw prototype at speeds of up to 16,000 RPM, although Skippy's ring screw will not be operating quite that quickly in order to avoid exciting the resonance in the screw rod. In Skippy, the main motor spins the rod and the nut travels back and forth. By the way, we are trying to commercialize the ring screw. More details at the end. Back to Skippy. The 2 springs are crucial to the performance of Skippy, and getting their parameters right was one of the most important aspects of the design process. Both springs are regressive, meaning that the stiffness is initially very high but goes down as the springs are compressed. Physically, both springs are fiberglass leaf springs curved into a circular arc, and both operate in compression. The diagram suggests that the mainspring operates in tension, but it does not show the true arrangement of this spring. In reality, the spring is not connected directly to the lever, but indirectly via a couple of push rods that reach from the lever to a point near the crossbar, which is where the spring is attached, as shown in this overlay. We chose fiberglass in preference to steel or titanium alloy because it has a higher elastic energy to mass ratio, and we chose it in preference to rubber partly to get the spring profile that we wanted, but mainly because we need repeatability, and rubber is not repeatable enough. We need repeatability so that Skippy can learn difficult acrobatic skills by practice, which is the same way that a human would learn them. The reason why the springs are regressive is different for each spring. In the case of the mainspring, regressiveness allows us to maximize the energy stored in the spring for a given stroke and maximum force. It also provides high stiffness at low force levels, which allows us to achieve high bandwidth control when the robot is balancing. In the case of the ankle spring, however, regressiveness helps to keep the foot firmly planted on the ground without slipping for as long as possible during the stance phases between each hop. At this point, you might be wondering why Skippy needs a spring-loaded ankle at all. The answer is that it allows Skippy to accomplish a clever trick. If Skippy is to make a controlled hop, then it must be able to reach the correct linear and angular momentum at the moment of liftoff. In the sagittal plane, there are 3 components of momentum: linear momentum in the horizontal and vertical directions, and angular momentum about the center of mass. But Skippy has only one motor to control them. So how can it control 3 independent variables with only one motor? Perhaps the easiest way to understand is to see what happens during a stance phase. Here is an animation of the stance phase going from a 2-meter hop into a 3-meter hop, slowed down by a factor of 30 so that you can see what is happening. The actual stance phase takes less than 1/4 of a second. Here it is again. This time, observe that the hip and ankle motions are out of phase. At the beginning, it is mostly the hip, and at the end, it is mostly the ankle. The point here is that torques in the hip and ankle joints push on the ground in 2 different directions, as shown in this diagram. The ankle torque is determined by the ankle spring and the ankle flexion angle, but the hip torque depends on the main motor. So the presence of a spring-loaded ankle gives the main motor the ability to alter the direction of the ground reaction force. This ability, together with the freedom to choose the hip angle and therefore foot position at the moment of landing, gives Skippy enough freedom to bring all three variables to their correct values at liftoff. This graph shows the ground reaction forces during the stance phase you've just seen. The bump near the beginning is caused by the hip joint hitting its end stop, which is relatively soft and springy in order to help Skippy to hop efficiently. The second bump is caused by the ankle joint hitting its end stop, which is harder and less bouncy than the hip end stop because bouncing of the ankle end stop isn't useful. Observe that these two events have different effects on the horizontal component of ground reaction force. The first makes a positive contribution, while the second makes a negative one. By adjusting the voltage signal sent to the motor, Skippy is able to alter the balance between these two effects, which allows it to control independently the integrals of these two curves. Remember that momentum is impulse, and that impulse is the integral of force. By the way, it is not necessary to hit the end stops in order to get this effect. It is always there, but hitting the end stops makes it easier to see in the graph. Another thing you can see in this graph is that the vertical ground reaction force peaks at nearly 350 newtons, which is enough to propel Skippy upwards at an acceleration of more than 10 g. This much acceleration is getting close to the saturation limit of the IMU's accelerometer. When designing a robot as fast and energetic as Skippy, one must pay attention to sensor saturation limits. This next graph shows the voltage signal sent to the main motor during this stance phase, and the current drawn by the main motor. The voltage signal begins as a sequence of 7 ramps of variable magnitude and duration, but is then modified in order to respect current and speed limits. As you can see in this graph, Skippy reaches all 3 limits during this stance phase. The voltage limit, which is determined by the battery pack, the current limit, which is determined by the motor driver, and the speed limit, which is determined by the resonant frequency of the screw rod, but which is also quite close to the motor's own speed limit. When Skippy hits multiple limits like this, we know it is operating at or close to its performance envelope. Another thing you can see in this graph is that the peak power input to the motor is very high. The main motor is a Maxon 70 watt DCX series motor, but the peak power input is more than a kilowatt. Clearly, Skippy can perform only a small number of maximum height hops before it has to stop to let the motor cool down. To know when to stop, Skippy's control software will have an accurate thermal model of the motor, supplemented with temperature measurements from a sensor placed on the motor's outer frame. In our dynamic simulations, we pay a lot of attention to detail. This graph, for example, shows the energy flows during the stance phase we've been looking at. Our simulations account for every energy input, every energy loss, and every energy transfer that takes place. The largest items in this graph are the kinetic energy of the mechanism, the gravitational potential energy of the mechanism, the elastic energy stored in the mainspring, the elastic energy stored in the ankle spring, and the energy lost in the motor due to the electrical resistance of the windings. All of the color bands below this one represent energy losses due to mechanical effects such as friction and damping. One of the things you can see in this graph is that the robot has a bit more than 60 joules when it lands, but the total energy has risen to nearly 220 joules at the moment of liftoff. This implies that the batteries have supplied slightly more than 150 joules to the robot in a time interval slightly less than a quarter of a second, which means that the average power consumption was slightly more than 600 watts. One can also see that about 90 joules were lost in various ways, which means that the energy efficiency of this stance phase was 40%. Skippy is more efficient when making smaller hops, and efficiencies above 60% can be achieved. Well, that's enough about hopping, so let us now talk about Skippy's other essential skill, balancing. Most of the researchers who have studied balancing have treated it as a control problem, but we need Skippy to be very good at balancing, and a robot's physical ability to balance is a property of the robot itself, not the control system. So we decided to treat balancing as a physical activity and to study it from a physical point of view. This approach has yielded 3 new results. The first is the idea of velocity gain, which provides a quantitative measure of a robot's physical ability to balance. Suppose we have a planar double pendulum, as shown here. The actuated joint angle is theta, and the center of mass makes an angle phi relative to the ground, measured at the support, and its horizontal coordinate is x. Its vertical coordinate is not important. All 3 position variables have corresponding velocity variables, theta dot, phi dot, and x dot. Suppose we apply an impulse about the actuated joint, shown here in magenta. This impulse will cause step changes in all 3 velocity variables, shown here as delta theta dot, delta phi dot, and delta x dot. If we treat this robot as a plant for a balance controller to control, then it is clear that theta dot can be the input, because this is the actuated joint, and so the control system has direct control over this variable. On the other hand, phi dot and x dot are both potential outputs, because the balance controller's objective is to control the horizontal motion of the center of mass. So we can define 2 possible velocity gains. An angular velocity gain, symbol g omega, which is the ratio delta phi dot over delta theta dot, and a linear velocity gain, symbol gv, which is the ratio delta x dot over delta theta dot. G omega has the property of being dimensionless and therefore scale invariant, whereas GV turns out to be useful in defining the plant, which is coming up next. The second new result is a remarkably simple description of the dynamics of balancing on a point, which is shown here in the form of a block diagram. We have found that if we design the balance controller to control this plant, then the resulting performance equals or exceeds the performance of the best existing balance controllers. But it is not yet good enough for Skippy. The state variable L is the angular momentum of the whole robot about the support point, and QA is the actuated joint's position variable. All 4 state variables can be calculated directly from the robot's position and velocity variables. The 2 gains, y1 and y2, are the only two parameters in the model, which means that the balancing behavior of the robot is determined by just two numbers. These gains depend on two physical properties of the robot: its linear velocity gain and its natural time constant of toppling, symbol Tc. The third new result is an extremely simple way to implement a behavior that we humans take for granted: leaning in anticipation of future motions. Suppose you want to open a heavy door. What do? You know that a lot of force will be required, so you lean back a little, slightly before you start to pull. This tactic of leaning in anticipation greatly improves the balance controller's performance, bringing it up to the level that Skippy needs, and it is really easy to implement. Suppose you want the actuated joint to follow this command signal. If we were to pass this signal through a simple first-order low-pass filter, then the output of the filter would look like this. Observe that the time constant of the filter equals the robot's natural time constant of toppling, Tc. This is important. Now suppose we pass the original command signal through the same filter, but with time going backwards. Now the output looks like this. This curve will make sense if you imagine time increasing from right to left instead of the usual direction left to right. Now, all you have to do in order to make the robot lean in anticipation is to use this filtered signal in place of the original as the command input to the balance controller. Here is an animation showing what it looks like, this time at full speed so that you can appreciate the speed and precision that the balance controller can now achieve. And finally, here is a video showing the performance that can be achieved on a real robot.